Now let's discuss one of the applications of ionizing radiation, the RTG, or the radioisotope thermoelectric generator, relies on a small amount of ionizing radiation producing material, specifically one that produces charged particles, alphas or betas, that heats itself so hot that you can harness that heat with a thermoelectric generator. Shown on the left is a diagram of one of these RTGs that's typically sent out into space to power deep space satellites. And on the right is a little sphere of the active element in this, plutonium-238, which a small sphere of it, about 3 centimeters in diameter, is enough to cause it to glow red hot from its own radioactive decay. The origin of this heat comes from the same decay diagrams that we've been showing you before. So shown here is the decay diagram for plutonium-238. Things that make good RTGs typically emit high-energy alpha or beta particles, and they have half-lives on the order of 10 to 100 years, meaning that they do emit quite a lot of radiation. They have a relatively high specific activity, but it doesn't decay so fast that the mission would be over before the probe even left Earth. To understand how these work, the idea is that heavy charged particles, or alpha particles as we've discussed, have very short ranges within matter, roughly 10 to 20 microns, keeping the energy inside the RTG and not letting it out. This energy is released in the form of heat, and that heat then goes into thermoelectric generators and radiative panels to help power the satellite and keep it warm. Now, an interesting thing about space is a very cold place, but it's actually difficult to keep things cool if they generate heat, because there's no air for convection to happen and there's nothing out there for conduction to happen, meaning the only way for heat to be transferred is via radiation of photons or optical light. So these radiator panels help release this energy in the form of infrared, non-ionizing radiation as the heat sink. Thermoelectric generators, like you see here, are comprised of little arrays of semiconductors and alternating positive and negative pellets that when you apply a large temperature difference across them, they actually cause a current to flow, like is shown here in the cross-section. So in this case, the RTG element, or the plutonium here, would get very hot. The other side of the thermoelectric generator would remain very cold, and that temperature differential causes a current to flow through the thermoelectric elements, generating a current and generating electricity directly. Hence the name thermoelectric, or electricity directly from heat. There are other isotopes that make good RTGs, as long as they fit those criteria that I discussed, like strontium-90, things that emit charged particles, in this case beta particles, and that have half-lives on the order of 1 to 10 to 100 years, about the lifetime of a good deep space mission. So you can leave Earth with relatively little material and get a lot of power out of it for a matter of decades. In this case, strontium-90 decays to yttrium-90, which itself beta decays into zirconium-90, which is a stable isotope. And so both of these beta particles actually contribute to the heat in this RTG. And these are awfully useful for unmanned lighthouses, dozens of which are on the Russian coastline way up in the Arctic Circle. Because they're great for places where you can't keep people, really cold remote outposts where all you want is a steady light. So these strontium-90 RTGs are typically in the realm of 50 to 350 kilocuries of radiation, and that's a lot of activity, producing about 10 to 120 watts of electrical power, and they're typically useful for 10 years. So they simply produce a light continuously and don't need refueling or maintenance until the activity drops too low. And there's lots of examples of these RTGs all along the Russian coastline, as you can see right here.